Welcome to our first invited speaker session this morning. Next to me, I have Dr. Paul Schenk, who is generously letting me use his microphone. So Dr. Schenk is a senior staff scientist at the Lunar and Planetary Institute. He's currently participating in the Cassini, Dawn, and New Horizons missions, and devoted most of 2015 and 2016 to the pioneering mapping session to the dwarf planets Ceres and Pluto. He has been responsible for mapping Pluto cartography and topography, and he specializes in impact craters and other features on icy bodies from Ceres and Pluto all the way to the icy moons in between, and in 3D imaging, which he uses to measure topography and create amazing views. So with that, please welcome Dr. Paul Schenk.
Greetings. I have a couple slides of introductory material about ourselves. I've been working for NASA for over 25 years now, close to 30 years now, but I actually got my start at a planetarium at the... I didn't create the planetarium, but they were gracious enough to let me use it for school classes and that sort of stuff. At the SUNY College at Buffalo, under Dr. Jim Orgren. Some of you may have known Jim, I don't know, but and if any of you are from Buffalo here today, I'd certainly love to meet up with you later on, and I see there are a couple of alumni there. I think that's an actual photograph of the old facility. They're actually rebuilding it, apparently. I just found that out yesterday. The Lunar and Planetary Institute, just a little bit of background for you. We're a nonprofit institute just off of Johnson Space Center in Houston, Texas, and we did survive Harvey. We have a lot of activities that are going on, and Christine, raise your hand, Christine is one of our staff members. We have education and outreach services. The things that are most of interest to you are probably the summer intern program in planetary sciences. We have historical archives dating back to the Apollo era, including all sorts of paper documents. You remember paper, it's this sheet of material with writing on it, that sort of stuff. And we also have a full staff of science researchers who cover the planetary bodies, including myself. If we don't know those planets, we know who can help you. And I actually graduated from WashU here in St. Louis, for those of you who are native to St. Louis. And as Anna mentioned, I'm a planetary mapper, and some of you may have actually used these things. Actually, I'm not sure. I have a pointer. Probably don't need one, but in any case, some of you may have actually used these. These are the color maps of the Saturn satellites, including the active moon Enceladus, which is on the left, and these are available for anyone to use, if you haven't used them already. And also, I am a specialist in 3D imaging, and I like to deep sea dive when I have the chance, which is not very often. So you really want to hear about Pluto, and you want to know how we got from the left to the right. And the left, of course, is one of the famous paintings by Chesley Bonestall, who didn't really know what was going on because nobody knew what was going on in the 1930s and 1940s, painted this craggy mountainous scene with ice on it. Was actually not too bad, actually, when you think about it. And most of you should know the history of the discovery of Pluto. It was found in 1930 by Clyde Tombaugh, who was resuming the search for Pluto's mysterious planet X. And for 60 years, we thought Pluto was a lonely outcast drift in the sea beyond Neptune. And in 1992, we found out that was not the case. The first of thousands, what turned out to be tens of thousands of objects in the so-called Kuiper Belt, this zone out beyond Neptune. And this represents a map a couple years ago. It's slightly out of date now, but it's more or less accurate. And we now know that Pluto is basically the first of many, the largest and the most interesting. Well, I shouldn't say that. It's very interesting, but it may not be the most interesting. We just discovered, for example, in a press release just yesterday that Haumea, which I don't think is on this map, Haumea, which is another Kuiper Belt object, I think somewhere around here, actually has a ring around it. So that was just published last week as a new scientific discovery. Pluto does not have a ring. However, it was obvious that it was weird from the very beginning. You saw in the last slide, it's highly inclined orbit. It's barely cold, about 35 degrees Kelvin, whatever that is in Fahrenheit. Cold. Colder than Buffalo. Colder than North Dakota. And starting in the 1970s and the 1980s, we discovered methane, nitrogen, and carbon monoxide, which are all gases here on the Earth, are all frozen on the surface because of the low temperatures. And in 1978, we found the large moon Charon, and 4 smaller moons, much smaller moons, just in this past decade or so. Pluto was not Planet X. It was much too small. In fact, in 1980, a prediction was published, and this is actually in the print, that Pluto would disappear. And I'll waste a little bit of time talking about this because it's really a really amusing read. I actually know one of these persons. The estimated mass of Pluto as a function of time actually was decreasing. Until 1975 or so, the mass was down here. If you follow the curve, as a true scientist would do, you assume that the measurements were correct because our colleagues don't mess up. You know, they do a good job. We trust them to do the right thing. That mass would actually disappear in 1984, which was an ominous year back then. Actually, seems to be happening today, actually, but. And actually would go negative in terms of mass. But anyway, this is actually, you can judge for yourself whether that is in fact a valid prediction. But it's actually, if you can find it again, it's actually in the journal EOS in 1980. It's actually a very entertaining read. So, just to set the stage before we get into the exploration phase, this just shows you the size of Pluto. This is the best view from Hubble as of 2014, before the encounter. You can see it's not very much detail. This is the other dwarf planet inside the orbit of Jupiter, Ceres. And this is also an HST. We've got much better for that, actually, to scale to the surface of the Moon. And then the 2 geologically interesting satellites of Saturn. Pluto's moon Charon is about this size here. And it's a little bit smaller than the Moon, but it's actually at least twice the size of Ceres, so it's much more interesting. The goal of exploring Pluto actually started very early in terms of actually trying to develop a plan, and that was in 1964. Some of you may have heard of the Grand Tour. It was an idea that was developed by a graduate student at Caltech, Gary Flandreau, who is now a teacher someplace, I think, to send that described the planetary alignment in the mid-1980s, where all the giant planets were on one side, and you can send a spacecraft that would ricochet from one to the other. It wouldn't actually ricochet, it would sort of be deflected from one to the other using one spacecraft and one mission. The plan was to send 4 spacecraft on 2 trajectories that would explore the 5 known planets in the outer solar system, including Pluto at that time, at the cost of $1 billion in 1970 dollars. And you can ask yourself how much is too much, because that was rejected for cost reasons, and a scaled down version, which was ultimately named Voyager, which you should have heard of by now, sent 2 spacecraft to explore only 4 objects, and Pluto was left out, but not for the last time. And those missions were obviously very successful. We're celebrating the 40th anniversary of the Voyager launch this summer. And by the time Voyager got to the end of its mission, it was originally planned to go just to Jupiter and Saturn. This was the official line, to go to Jupiter and Saturn, and if it was successful in all its objectives in the first flight, the second flight, Voyager 2, would be granted the permission to extend the mission to Uranus and Neptune only if we got everything at Saturn. And fortunately it did, and through the trials and tribulations of Voyager, it got there, and this is a montage of various images put together showing the crescent Neptune and the ring system. I put that one together as one of my first things. Right around that time, people realized, yeah, we're completing Voyager, but not really. We're missing one. So there's a grassroots effort that was launched. A person by the name of Alan Stern was one of the leaders of that effort, and his name will crop up again. To finish that job and get to Pluto, it would require a separate mission, of course. Voyager was well on its way. So New Horizons, as it was named, was selected in the year 2001. And 4.5 years later, it was launched, January 2006. I have some videos I can show you later on. I want to make sure that we don't have any hiccups, so I'm going to save the videos for last. But I do have the launch video, which is always fun to watch a launch video. And here's the spacecraft. You know what the grand piano is. We have one out in the hallway. New Horizons is the size of a grand piano, or a Yugo, or a, what's that East German car? I can't remember the name of it right now. But anyway, so this box here is the main electronics package. It's about the size of a, as I said, this is the radio antenna. It's even smaller. Various instruments on board. These detect solar wind and energetic particles. The high-resolution camera is called Lori. The color imager and IR spectrometer is called Ralph. I didn't name these. Alice is the UV imaging spectrometer, which is primarily used for atmospheric studies, and Pluto does have an atmosphere. Radioisotope thermoelectric generators. Student dust counter, which does not count the dust of students. That would be a lifetime job. But having been a student, it was, however, built by students at the University of Colorado, and it was the first time such an instrument had been launched on a spacecraft to deep space. So it was of some interest. So everything went well at launch. Immediately after that, Pluto was left out again, and we're not going to talk about that. It'd take too long. About a year after launch, we passed the planet Jupiter for a gravity assist, which shaved about 3 years off of our flight time, and got some exciting images of Pluto and its erupting moon Io. It was a very successful encounter. It also exercised the team, got them used to planning, because we had 8 long years of coasting with nothing to do but plan the Pluto encounter. And right around this time, actually, we did a full dress rehearsal of the encounter plan, where the spacecraft fired its thrusters, took pictures, and did its rotations, and did the whole sequence, except, of course, there was no Pluto. So it was just a chance for us to test the sequence to make sure there were no glitches or things that would cause the spacecraft to stop its procedures. And that was very good. So this is the plan. This is the Pluto and its large moon Charon, and the 2 largest of the small satellites. This was made actually before we discovered the 2 really small ones. And this is the trajectory, and this is 11 o'clock that day, and this is 12 o'clock. So that's a time span of an hour. So you can tell we're moving pretty quickly, 15 kilometers per second. And we go through the occultation tracks, or shadows rather, of both Pluto and Charon, because we want to know how dense the atmosphere is and what it's composed of. Those were very successful. And throughout this entire time period that you see in the slide, the spacecraft was incommunicado because it was busy. We arrived early, and of course, in the modern era, selfies are the order of the day, so those are some of me, of course, just to prove I was there. And we were watching each day as Pluto arrived, and there was actually a safing event 7 days out where the spacecraft stopped what it was doing and said there was a problem, and fortunately the people running the mission actually knew what they were doing, and they got it back on track within 3 days, and we were taking pictures again. This is one of those. It was nail biting, of course, but you can tell from this sort of image that Pluto doesn't look normal. It doesn't look like anything we've seen before. You can't even identify craters, so it's enigmatic and tantalizing, but we really didn't know what was going on. We were scratching our heads, I'm telling you. Encounter day started for us about 6 a.m. when we received this what we would call the full frame image, and is the last image that we acquired before the encounter, before we started the main sequence where the spacecraft was doing everything every minute of the day and couldn't take the time out to radio back to us. If you do that, you lose observation time, and we don't want to do that. This is a cleaned up image taken when we got the full data set back. The original was highly compressed. And if you've seen JPEG artifacts, the entire image was full of JPEG artifacts. The reason was because we're so far away, it takes so long to transmit an image. We only wanted a browse file just to see what New Horizons was seeing, to monitor what it was doing, and to see something of the planet, even if it was a compressed image. This image and images like it gave rise to the famous Heart of Pluto graphics that people were making in those days. And this is the bright feature, which is now called Tombow Regio, this basically bright patch on the surface, half of which is this feature here, which we'll see again later. But we had the entire day with nothing to do except wait around, because the next images that were going to come down were the high-resolution images, which New Horizons hadn't even taken yet. It was going to take them during the day, and they were going to be targeted right here. So keep those in mind. Those are the ones that we were going to receive first the day after. As I said, we spent the encounter day just sort of wandering around waiting for the event to happen, and there were lots of celebrations. There was lots of media interviews that were going on. We had about 250 members of the media there that day. That's my thesis advisor, who actually lives here. He's in Washington University, Bill McKinnon. And then the long-awaited phone home moment, which was at around 8:35 or maybe it was 8:55 that evening. All the team gathered, and again, New Horizons wasn't going to talk to us until it had completed the main observation sequence, and I was going to turn the antenna to Earth and say, "Hi, I'm here. Everything worked," or not. So it was a nail biter. We had confidence, but it was our only chance. If we missed it, no Pluto. We wouldn't get anything other than that last shot that I showed you just a moment ago. So everybody was nervous, and it was more than 10 years worth of planning and effort. And you can actually watch this video. I think it's on YouTube. It's the New Horizons phone home. The moment when we got the signal, and you can see as they read through the telemetry that indeed everything happened as it was. They recorded the data. The spacecraft didn't burp or have any hiccups, and everybody was all very happy and stuff. So then we went to bed, because we weren't going to get anything until the morning. And that's what came up on our desktops at 9:37 a.m. on July 15th, the day after. And we knew we were going to get in the center of that bright heart feature, and we knew that there was something unusual going on there, but we didn't expect this. This looks like porridge on the stovetop that's sort of bubbling and boiling. I actually see this sort of pattern when I'm having miso soup at the Japanese restaurants. This sort of cellular convection pattern is dramatic. These cells are about 30 to 40 kilometers across. You could probably fit St. Louis in the largest one. So it's very extensive. And then there's these small mountains cropped out in the middle of that ice sheet. Very dramatic sort of texture. But it does look like an ice sheet that's convecting, and that's in fact what it is. We later determined that this ice is composed of nitrogen, carbon monoxide, and methane all mixed together, but primarily nitrogen. And the next shot that came down was at the southern edge of this bright deposit down at the bottom. And there are these tall mountains, 3 to 5 kilometers high, poking up above this smooth sheet. And that was our first hint that there are different materials on Pluto. Nitrogen ice, even though it is frozen on the surface, is still so volatile that it will flow under the conditions of Pluto, 35 Kelvin. And that's exactly what it does. That's why you see those cellular convection patterns because the ice is actually overturning even as we speak, even under those conditions. But water ice, even though it's a glacier here on Earth and will flow downhill, is like granite on Pluto, rock hard. Hit it with a hammer and it'll just shatter, and it won't flow at all under Pluto conditions due to the extreme temperatures. And that's what these mountains are composed of. These tall mountains stick up, their slopes are like 40 degrees. I mean, they're really steep slopes. And it tells us that there's two different kinds of materials on Pluto. There's the bedrock, and then there's the soft glacial type ice that we see on the surface. And it has consequences. The next slide, now we can only return a couple images, even in browse format. We can only return a couple images a day during the first week after the encounter. So we carefully chose those in advance. What do we want to see most to get a flavor of what New Horizons saw? The first was the center of that ice sheet. The second was Charon's moon. We want to know what it's like. So this is what on top you see the approach image. You can see that there's structure within it, and there's also a dark polar. This is where the North Pole is actually. See there's a dark reddish cap there, which is unusual. We see these enormous canyons, fault-bounded blocks, all sorts of fractures all across the surface. And then down here to this, which actually turns out to be the south, everything's on its side in this view, because this is the way the images were returned. There's these smooth terrains here. Obviously, there's been a lot of resurfacing. On Pluto, there's been heavy fracturing and lots of volcanism. We were sort of afraid Charon would be a boring cratered world like Rhea is at Saturn. Although Rhea has its fracture systems too, as it turns out. Cassini discovered lots of interesting things there, which we don't have time to talk about. But Charon is geologically complex, and we're very happy about that. We didn't want a boring body in our Pluto system, and we didn't find that. The next day, we got the high phase images because we were interested in something about the atmosphere, and we learned a lot in this image. But when we saw this image, a lot of us just sort of sat there and just looked at it. It's just really pretty. And sometimes you just got to stand back and forget the science and just admire the scenery, you know? But what we were not expecting, we were just simply not expecting this. We didn't know what we would see, what type of atmosphere. We knew it was thin, sort of like Mars, but we didn't really know. Is there a haze layer? Is there no haze? And this showed us that there is an enormous amount of haze in the Pluto atmosphere, extending about 150 kilometers into space, at least. And if you look carefully, you can actually see it's layered. There's structure within it, banding. But fortunately, we can see through it. It's not an obscuring haze like it is on Titan, where you can't see the surface at optical wavelengths. So that was very nice. Oh. Now, that was the first week. Then we had a little bit of a hiatus, a month, where we're getting all sorts of engineering data down from the spacecraft. The full playback at uncompressed conditions started in September and lasted for 11 months, simply because the antenna is small and the distance is like 40 AU or something like that. So it took a long time to get the entire data set down. But when it did, we got a lot of surprises. And one of them was this crescent view. You can see there's some detail up here. Similar to the view we had before, but at much higher resolution. You can see there's lots of interesting structure here. These are those very same mountains I showed you just before, except we're looking at it from behind. You're looking basically into shadows. The sun's off up in the ceiling somewhere, but you see the structure in the haze here. There's also some bright structures here where sun is sort of glinting off the ice, as it were. These would be some of those smooth deposits. And this is that ice sheet again. It's all sort of glaring at you like a terrestrial ice sheet would. Then we got the highest resolution images down later that winter. And this is probably one of the highest resolution images we got, 80 meters resolution. So this is about, I would say, the size of the city of St. Louis itself, rather than the environs. So you see all these small pitted structures here. We still don't know exactly why they form. They could be wind erosion scouring out the ice, because it's still volatile even in Pluto conditions, revealing some dark material at the bottom. These are a couple kilometers across and a few hundred meters deep. So small towns could fit in them easily. but large areas of the ice sheet are covered in this sort of terrain. And it's still a bit of a head scratcher. On Charon, this is the highest resolution view we see, and this is that smooth terrain that we saw in the lower resolution images, but it's got a lot of structure in it. There's fractures that cut across it. There's impact craters. This one's about 15 kilometers across for scale. And then there's these erosional pitting features that we see in this area here. Probably just erosion due to sunlight, even though the sun there is about 150 times less powerful than it is here. Then there's these mountains here that stick up above those plains. These are about 2 to 3 kilometers high. Those are probably blocks of Charon's crust that have actually foundered into the interior, and you're seeing only the tips of those remaining standing up above the surface. So they're buried underneath this smooth deposit. This vast area covers the southern hemisphere and has resurfaced it in some sort of icy lava, possibly ammonia water mixtures. Because we do see ammonia on Charon. It's one of the few places where we do see ammonia. We did get some views of Pluto's 4 other small moons, and this is Charon for scale. So these are only about 20 kilometers across. The largest one, these are only a few kilometers, and we didn't get very good views of those. We got a pretty good view of Nix, and we do see some impact craters on it, but we only see features about 300 meters across. There's a large crater with a dark red stain on it here. Not much we can really say about them. There's some hinting of fracturing within the moons, but we didn't really get a close enough view to see that. We did see these, and those are the best views. So, what did we get from Pluto and what did we learn? We've seen some of that already. But one of the things, in particular, is the things that I've been responsible for is mapping. And these are the global maps of Pluto. We'll start with Charon. This is just a little blow up of this area here, just to show you the quality of the map. And this is full color in 4 colors, at least. The colors, there's a spectrometer which goes out into the near infrared well into it, but the high resolution mapping camera had 4 colors that were red, blue, red, near infrared just beyond the red, and then a methane filter which was at about 809. It has 2 filters just beyond the red in the human range. So we see that here. You see the dark red polar cap up here. These are in cylindrical projection. And then the topographic map where reds are high and blues are low. So there's about 20 kilometers of relief on Charon. It's a very rugged place. And you can actually drop these into Google Earth. This is a screen capture from that. Anybody can do that. The maps are available online. They're on the NASA websites, or else you can just ask me for it. There's a dark polar patch, which actually we believe is due to atmosphere escaping from Pluto, and it migrates to the poles because of the sunlight and the temperature differences at the poles of the 2 bodies, leaving a sort of dark reddish stain there. This is the topographic map, so you can see that this is the low area. This is a crater which we informally named Dorothy Gale. But here's the fracture system, and there's a fracture system over here too. So it's, and you can actually see there's additional fractures out in this region as well. This is the lowest area here. It's about 14 kilometers below the mean topographic level. It's astonishingly low. In fact, it's got the most rugged relief of any icy body of this size, including the Saturnian and Uranian satellites, except Iapetus. Iapetus is even more rugged, but it's the only one. The maps of Pluto, this is the current best map using all the best images. You can see that there's color variations. There's this yellowish stain at the North Pole, which is due to methane. And then there's this equatorial band, which is sort of a dark reddish color, probably due to organic materials that are converted from methane. You can see there's also these irregular patches of sort of has a greenish cast. Those are actually elevated plateaus, which are known as bladed terrain, and I realized I forgot to put a picture in of those. But I can show them to you later. And this, of course, is that ice sheet that we saw the convective patterns within. This is mostly nitrogen with some methane and carbon monoxide in it. And we'll see that in the next two slides. It's a very unusual material. We can actually map the distribution of the ices, different ice phases, and where they're most concentrated. This is a map of where the nitrogen ice is, and sure enough, it's right in the middle of that area, that elliptical area, which we call Sputnik Planitia, Planitia being a low plane, but it's named after the Sputnik mission. And there's also some nitrogen ice up here. This shows the distribution of methane ice, and it shows it at the pole, but also in the ice sheet. And we can do that for carbon monoxide and for water ice, and maybe a few other things as well. But this just shows you a hint of some of the things where they are. And looking at the topography, again, blue is low and red's high. There's a dome at the North Pole with a fracture in it. But this is that ice sheet, and it's a large depression, 3 kilometers deep, flat line, filled with nitrogen ice. And we believe that this is actually a large impact scar. Those of you who are familiar with Mars know the Hellas impact basin, large structure, very deep. So we think this is analogous to that, a large, very ancient impact structure on Pluto. And then because it's low, the atmospheric pressure is high, and the temperatures are maybe a few degrees warmer, I'm not entirely sure, but it's the pressure that makes the difference. So that forms a place where nitrogen ice is more stable, and it sort of migrates from the rest of the surface into this low, this really deep low, and trains other ices with it, the carbon monoxide and the methane, and that's why you get these signatures here, is because that's a low, and that's where the ice accumulated. We saw some other things. We saw this large circular structure, which is about 150 kilometers across, depending on where you measure it, and with a large, deep pit in the middle of it. So it's about 3 to 5 kilometers deep, depending on where you measure it, and high, 3 to 5 kilometers high, and it has almost no impact craters on it. It's a very young surface. And we think this is some sort of volcanic extrusion that came up from the interior. It looks very different than you would think of Mars or the Earth, but you have to remember that these are ices. They're methane, they're ammonia ices, and so they're going to behave a little bit differently than granites and basalts and other volcanic materials. And there's actually another volcano just off the scene here, and you can see the northern margin of that as well. These, again, are those mountains that you saw in one of the very first slides I showed. But there's this amazing structure here. Enormous amount of volcanic material has come to the surface. We also see evidence of a lot of glaciation. I mentioned that nitrogen, even under Pluto conditions, can flow, and that's exactly what's happened here. This is the edge of, over here on this side is the edge of that raw, vast ice sheet that's in the depression. And to the east of it, to my side, is a high plateau that stands about 3 kilometers above the ice sheet. And you can see these valleys that are being carved into that plateau as nitrogen ice flows off of it and goes into the depression. Much like the ice flowing off the coast of Greenland into the sea, except in this case it's a circular basin rather than the Atlantic basin. You can see some material flowing off the canyons here to the south as well. And we don't know what that is. That's not even an impact crater. That's some sort of explosion pit. So there's a lot of glacier activity going on. You can see another example of it here. This is a mountain range. Enrique Montes is our informal name for it, named after an explorer of some sort. About 200 kilometers long, about 40 kilometers wide. It sort of looks like the Alps. In fact, that's what it is. It's a mountain range that's deeply carved by valleys, more evidence of glacial flow. And you can sort of, if you squint your eyes or look really closely, you can sort of see them. It's a little bit dark here, but there's lots of valleys to the sides. But it's also capped by snow. But it's not water ice snow, it's actually methane snow. In fact, all the purple material here is methane, and it correlates with the bright material you'll see, which correlates with high points on the surface where the atmospheric pressure is lower. In this case, that's where methane is most stable. At these latitudes anyway. So I like to say that that's a good place for skiing. So all in all, not quite done yet, but all in all, it was a fabulous ride and a great team, and we had a wonderful summer watching Pluto unfold before our eyes. This was in July of 2015, before we had gotten all the high-resolution images down, where we had just seen those previews, and we were breaking up, going home to our home institutes. This was actually in Maryland at the Johns Hopkins Applied Physics Laboratory where the mission was run. But Pluto, New Horizons is not done yet. After Pluto, the mission charter read, visit Pluto and beyond. Beyond being the Kuiper Belt, that zone of thousands of small objects that orbit beyond the planet Pluto. And there's Haumea, which is the one that we just found out has a ring on it. So we were looking to see what could we visit next. And it was a challenge because, as it turns out, this, we had to look from Earth in this general vicinity, which put our target in the center of Sagittarius. Now, if you know Sagittarius, you know it's kind of a crowded star field. That's an understatement. So we didn't actually find a target until 2014, a year before we got to Pluto. And the only ones we found that we could reach with our thrusters, because we have to deflect a little bit to get to it, are targets that we call PT1 and PT3, which were on the track, and they had they were in this position in the solar system. And we chose one of those, and we may have chosen wisely. The target turned out to be rather small. Both of them turned out to be very small. This is an estimate of the size of the object as of last year. And you can see the trajectory. We just passed Pluto, and there's our target arrival time in January 1st, 2019. But you can see the size in comparison to Cape Cod. It's only about 25, maybe 30 kilometers across if we're lucky. We still don't know very much about the target because it's so small. It's like 25th magnitude or something like that, if I remember the number correctly, maybe 24th. We did have the good fortune to, after two false attempts, or two unsuccessful attempts, to actually get stellar occultation across this object. And this shows the, in a graphical format, the traces of the occultation. These tracks missed the target, whereas these tracks actually were occulted. And you can see that it's a very irregular shaped object. We think it might be a contact binary with two objects sort of touching each other, maybe. It may be more complicated than that, probably, because this is just one single occultation event. But we were very happy to successfully get it. It's the smallest and most distant object that we've ever observed using stellar occultation techniques. So we were very fortunate to get that after two missed attempts. The reason we missed it was because it's such a small object that our knowledge of the actual position was not precise enough that we actually missed the occultation track by about 100 kilometers in each case. But Hubble got some observations before this one and allowed us to fine-tune the orbit, and bingo, we got it. So we will see you then on January 1st, 2019, which is just a little over a year from now. And we're planning the observations now, so we should get some very good images of this target. We're hoping for resolution possibly better than 100 meters. So now we move to the video phase, and I got a couple videos. And who doesn't like the launch video?
And liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
Hard to believe this was 2006. But it took 9.5 years to get
That's
there.
15 seconds. Everything continues to look good. As
It's the only launch
atmospheric
I've ever
vehicle
seen,
strives away
and
from
I was
Florida's
just
east coast,
amazed. It just leapt off the
five solid
pad.
rocket
Just
strap
couldn't wait to
boosters
get
are
there.
burning
It's just
just fine, sending
like
the New
no
Horizons
slow
spacecraft
lumbering Saturn Vs.
on
This
its way
just
to the
leapt.
very edge of
Just
our
like,
solar
boom.
system.
And let me see if I can move on. Yes, okay. Now, we can take those data sets, and you guys can do it. Some of you already started, I think. Take them, the topography and the color map, and this is what we did at the Institute. And it's a little dark, but I think it'll brighten up. We're coming up from the south, going over those mountains that we saw in that early shot, those tall 3-kilometer, 5-kilometer mountains, and then the ice sheet. You begin to see the ice sheet. And you'll see on the left side, you'll see some impact craters of the eroded glacial terrain, and we'll pass over the glaciated terrain at the end. We'll come close to the North Pole. This is not exaggerated much, maybe a factor of 2, maybe 3. and then there's a nice glacier-filled crater there. We're coming up towards the pole. I don't think we cross over the pole in this shot, but we come close to it. It's off the side here. Some interesting structures there. Fracture system coming in through there, another crater. That's that yellow stain, yellow snow, which is due to methane in this case. Some eroded structures here. This is deeply pitted, several kilometers deep. These are an eroded crater as well. And then up here, actually, we'll see the bladed terrain I mentioned as well. Those are high-standing plateaus, several kilometers high. There they are, right there. And if you look closely, you can see the finely striated structure along the tops of those plateaus. Those are high-standing. We don't really know why they're there. They form in equatorial areas, and we could even watch that again, but let's watch the Charon one, and then we can always go back to that. I think the Charon one will be the last one. Yeah, this is Charon, the satellite. You see the fracture system coming across here, across the, it sort of follows the equator mostly. This is the smooth terrains that have resurfaced the southern hemisphere. We'll fly over that at the end. Again, this is using the color map draped on the topography. The Star Trek shot. Should have used this in the opening for Next Generation, right? That's that north polar cap I was talking about earlier, the dark stain coming off the atmosphere of Pluto. And then we'll fly over the smooth, resurfaced terrains in the southern hemisphere. Again, the fracture system that's broken up the northern areas. And with, let's just do one more, since I got a few minutes, I think. And then we'll go to questions. I'll be here all afternoon through lunch, so if anybody wants to talk more about Pluto, we can certainly do that. And this just shows the rotation of Pluto. You can see the low resolution view here. That was on approach. Pluto has a 6-day period, so that when we're approaching, we never really got a good look at the backside again, due to our high rotation rate. I'm sorry, high approach velocity. Let's watch that again. So with that, I'll open it for questions. I think we've got maybe 15 minutes for questions, I think. Yes?
My question is, there's beautiful, is it a Tomball, what did you call it?
Tomball Regio, named after Pleiades, the discoverer.
And you said that basically like deposition places for this nitrogen, what type, because of a pressure difference, do you know how many millibars different that is? Or, I mean, because when we talk to our audiences, it exists because of this small difference. And could you give us an analogy or something we could share with people?
An analogy.
Little things matter, and this could be an example of little things matter.
I don't deal in atmospheres except I breathe them. So I can't tell you, the mean surface pressure is similar to what you see on Mars. I don't know what the difference is when you're 3 kilometers below that, but it's not a difficult number to find. Something on Earth. I think you see it on Mars, but that's not really a very useful analogy. It's still extraterrestrial. I don't know, maybe somebody else in the audience can think of something. I'm sort of stumped right now for a good answer to that, but let me give that some thought. Yeah, in a sense, you see that sort of thing on Earth where where it snows in the Rockies. You can see it from Denver, but it's raining down in. It's sort of like that, and I guess that's the best I could come up with, except that of course this is you're precipitating rather than a solid rather than a liquid at the deeper pressures. Yeah, let me give that some thought. But yeah, you do see lots of pressure differences. And yes, in fact, I've been in the Grand Canyon where it was snowing on the top, and the next day I was down at the bottom when we were in shorts and stuff. So yeah.
What kind of temperature variation across the planet?
Not very much. Ooh, you guys, this is a tough audience. Diurnal temperature variations on Pluto. Because we're at 35 degrees, that's an average. It can't get too much lower than that because we don't get that close to absolute zero. We're talking only about 10 or 20 degrees difference. Pluto has a very long season, of course, because it's in a 250, or well, Wikipedia will tell me, but it's it's like 200-year orbit, and right now it's actually its pole is tilted towards the ecliptic, so it's like Uranus. It's flopping on its side. In the 1980s, it was actually the pole was directly No, the pole was straight up. That's right. No, the pole was. Oh, I don't remember anymore. At this time, the southern hemisphere below about 45 degrees latitude was in total darkness. It's actually moving, I think, where the pole is going to be facing towards the sun, so only one hemisphere will be visible in sunlight. That's going to warm up that hemisphere, and the unlit hemisphere is going to be in perpetual darkness for that season, and it's going to get very cold. It's going to get very close to absolute zero. I don't know the exact numbers. So the temperature extremes can be very, very large on Pluto if you're a Plutonian. But for a terrestrial person, the temperature variations in an absolute number of degrees isn't going to be that large. But yeah, it'll get very bitterly cold in the southern winter, which we're approaching, and very warm at the North Pole, where it's getting to be northern summer. So, yeah. And I'm going to move across this way, I think.
Yeah, well, if Wikipedia is the believe, and it was saying it's 33 for the minimum and maximum 55.
Okay, yeah. Not that I could go to the North, yeah. That makes sense. I'll go there. Okay.
You just mentioned one of your global maps. You used the word organic matter.
Yeah.
So what is that composed of?
Nobody really knows for sure. We didn't really have the sensitivity to pick out a large number of organic molecules. But we call it something, we give it a name called tholin. And tholin, Tholin, is a mixture, basically, of organic materials that are byproducts of photolytic sunlight, alteration of methane. Methane is unstable to sunlight over long periods of time, and it will sort of bond with other materials, the nitrogen and the water ice and the other things, and create a sort of complex mixture of hydrocarbons, which we didn't have the sensitivity to really measure a lot of. But that's basically at a sort of like a brown organic goo. It's not a very technical answer, but that's the best we can give you. I'll go there.
Volcanoes are something.
Yeah.
Where are they relative to this? And then are there any of those mechanisms for how they're or were?
The ice volcanoes are right about here, just off the southwest flank of the large impact basin and ice sheet that fills it. The second half of your question is very good. We don't really know the answer to that one either. We saw a lot of interesting things on Pluto that we still don't know the answer to. My suspicion is that you're mobilizing ammonia-rich water ice mixtures. When you mix ammonia and water, you get ammonia hydrate. Makes sense. Which has a lower melting point. It's easier to melt than water is. And there might be enough heat, residual heat from the impact perhaps, that mobilized enough of it to actually extrude it onto the surface. Why it took so long for that to do it is something we don't understand. The impact that we think formed this is like 1,500 kilometers by 1,000 kilometers across, but it's very ancient. These volcanoes are really very young.
Are they still active?
We didn't see any activity on them, but they have almost no impact craters in them, so that they're young geologically to us. They could be 100 million years old, but that would be geologically very young. I'm going to go over there, lady in red.
After you finish the mapping process,
Yes.
what is the next step for you as a scientist? What are kind of your burning questions that you would like to explore, given the data that you have?
Well, answer the questions you've been asking me, and I can't answer. Well, we're busy preparing for the flyby in January 2019. I've been looking at impact craters to try to compare how they relate to other bodies and what they tell us about the impact crater process. We want to look at this giant impact structure and sort of figure out how old is it, what effect did it have on the interior, because that's a large structure and it really had a profound effect on the planet. In fact, we think that it originally formed elsewhere, but because it's a topographic low, it forms a gravity anomaly, a gravity deficit. It actually moves, it forced the shell of Pluto to actually rotate around. This point, for example, is directly opposite the moon Charon, which is the place it would go to. The volcanic feature, we've got several people on the team who are looking at that, mapping how high it is, what volume is there, what viscosities of material are implied because of the shape. If it's viscous, that means it's possibly one composition, but if it's low viscosity, it means it's a different composition. We're looking at the distribution of these materials. The dark material forms only in the equatorial zone, for example. Why is it there? Why is that organic goo that I just described, that we don't know the exact composition of, why is it formed only there? Why not at the poles? Right? So there's all sorts of questions to answer.
Can you hypothesize what the volcanoes
I mentioned Hellas on Mars, which is a very large structure, like 3,000 kilometers across, something like that. And on the flanks of it, just on the southern and the northeastern flank especially, there are two large volcanic complexes that are much younger than the impact basin. And it reminds us of this similar situation where we saw that volcanic complex just off the southwest flank of this structure as well. Maybe there's something in the impact heat. When the impact forms on a large impact like that, forms on a planetary surface, it delivers a lot of heat. It's impacting at several kilometers per second. It delivers a lot of frictional heating into the surface. That heat may take a while to dissipate. It may form like a pocket of melt underneath it, and that melt kind of finds its way to the surface after a long period of time. That's a speculation. We're still trying to figure that one out. We had some questions in the back. I'm going to move to the back and then come to the front here. Somebody else is going to have to tell me when we need to leave, of course. Yes. I'm sorry.
How long did it take to form?
How long did what take to form? Since we're not sure the exact age, it's difficult to say. It could be a couple thousand years. It could be a couple million years. On Earth, volcanoes form in a matter of tens of thousands of years, million or so years maybe.
We have time for one more.
Yeah, on the aisle there, yeah.
What's the source of the heat for that convection?
He's referring to the convection pattern that we saw in the heart of the bright spot here, that looked like miso soup sort of thing. And there's dozens of these convection cells. Probably a combination of geothermal heat from below, and even though Pluto's out the distant edge of the solar system, there's still heat coming from the inside, with a little bit of solar heat falling onto the ice sheet from above. Nitrogen, as I said, is very soft at these temperatures, and will flow. We saw the glaciers. So geothermal heat is probably enough from the base to create a sort of convection over on the ice sheet above the surface. We think that the ice sheet is probably on the order of maybe 3 kilometers thick at most. Give or take a kilometer or so, because we don't actually we don't have radar to sound the bottom of it. So we have to sort of make educated guesses about that. So that actually is thin enough, or thick enough, I should say, to convect due to the heat coming from below. So that probably is as good an answer as I can give you right now. But yeah, there's enough heat to do it, just from the heat coming from the ground.
Thank you very much, Dr. Schenk. We appreciate you coming out and talking to us.